So let's take a look at Schrodinger's cat. I would suggest that not many of us really understand what is going on. First of all then, let's be clear that Erwin Schrödinger impressively came up with a wave equation that enables us to understand particles at a very small scale, such as electrons and atoms. Let's understand better what the wave equation is, or rather what the wave function is. So here I'm showing an example wave function psi of x, and all we really need to understand for the purposes of understanding Schrödinger's cat is that a wave function corresponds to the probability, for this particular example, the probability of finding a particle, such as an electron, at a given position x. So that's what I'm showing in this animation here, where we've actually got a time-varying wave function. But what we can do for simplicity is just freeze that in time, and then the wave function is saying what is the probability of finding a particle. Here's a kind of a box with a wall in the middle, and we see that one single particle might be found on the right side of the box or the left side of the box. And the wave function tells us that there is a non-zero probability of finding it to the left or to the right inside the box. Now, you'll notice that there are in fact infinitely many positions x where that particle could be found. And the key point to understand is that it's only when we make an observation or a measurement of a particle's position, only then do we find a very specific value of x, the position. So let's take a look at that. When we make a measurement, you'll see that that wave function has now collapsed to one particular example of sampling that probability function, and so with a certain probability here we found the particle is located at that position x, but it could of course have been found either side of that dividing wall, and indeed with small probability could even have been found close to the walls of the box as well. So let's take another look at that. This is the well-known example of an electron as a wave function passing through a double slit. And then we see, this is a time-varying wave function, we see that the electron as a wave function simultaneously is in existence to the left of the slits and also to the right of the slits. And furthermore, because the electron is a wave function, we actually have an interference pattern, which is really remarkable. Let's take a look at a profile for that interference pattern. This is an example of what a profile might look like. And again, it's telling us what is the probability of finding the particle at any given position. And so here you can see it's got high probability of being found there, high probability here, low probability between those peaks. So that's also what this is indicating: low probability, high probability, low probability. Now, that is an example of a quantum superposition of states, whereby the electron is simultaneously in all of these positions, infinitely many positions. That is the remarkable phenomenon of quantum superposition. And it is only when we actually make a measurement, such as that one there, that we get a specific location that is now locked in for where that electron is actually located. It is no longer in these infinitely many positions. It is now fixed to one particular location. So here, if we were to make many measurements, here I'm using a dot to indicate a measured position of the electron. Here are many, many hundreds of electrons being detected, and each time that wave function is collapsing when we make a measurement of the electron position, of the position of an electron, and that's what that's indicating. So that's all very interesting, but it was obviously a concern to Schrödinger, as we can see from his famous cat thought experiment, where this is the situation. We have a cat inside a box, a closed box. Then we have a radioactive source here, which either will decay or will not decay at any given moment in time. And so that is a quantum superposition. Just like in the previous slides, we've seen a particle can simultaneously be in many positions, and it's only when we measure it that it collapses to a particular fixed position. Likewise, this radioactive source, only when we make an observation of it as to whether it's decayed or not decayed, only then will we find out if the radioactive source has or has not decayed. But prior to measurement, it is in a quantum superposition of both states. So In the cat experiment, this is the profound consequence of that. We actually have this configuration whereby if the radioactive source decays, then poison is released into the box and the cat dies. If, though, the radioactive source does not decay, there is no poison released and the cat remains alive. Now, just as the radioactive source is simultaneously in a quantum superposition between decayed or not decayed, therefore also the poison is simultaneously in a state of released and not released, and therefore the cat is simultaneously in a situation of both dead and alive. It is only when we make an observation by opening the box to see what has happened that we either observe the cat is dead or we open the box and observe the cat as alive, and in which case this quantum superposition has now collapsed into either one definite outcome or the other definite outcome. The profound consequence, though, is this situation here of quantum superposition. Prior to the measurement, we have simultaneously a source that has decayed and not decayed, so likewise, simultaneously, Schrodinger's cat is both dead and alive. Now that might seem like a very wild idea, but just think about it. Quantum computing, a reality these days, relies exactly on that principle of having quantum qubits, a 1 or a 0 bit, that is simultaneously a 1 and a 0. And it is that that makes quantum computing so immensely powerful. So I hope this has helped you to understand Schrodinger's cat a bit better. Thank you very much for listening.